Hello, today I'm going to introduce an interesting and practical topic in artificial intelligence, object detection. So what is object detection? It is kind of AI technology related to the computer vision and image processing that deals with detecting objects of a certain class or category, such like humans, animals, vegetables, fruits, cars, in digital images, photos, or video frames. So well-researched areas of object detection including such like people detection, face detection, and car detection. So it is fundamental for many downstream computer vision tasks, such like the object tracking and object counting. So the objective of object detection is to solve the problem what objects are where, and also it aims at innovating and creating models to provide the key insights for the AI-based applications. There are many use cases across various industries. It plays a vital role in understanding the things which is popular in the retail, security, transportation, medical, agriculture, as well as military. So the applications including autonomous car. For example, Tesla's autopilot AI heavily utilized object detection to perceive the environments surrounding the car and also detect any threats such like the oncoming vehicles or the obstacles. Besides the driverless car, also application includes the pedestrian detection, image retrieval, video surveillance, parking management, car number plate recognition, people counting, face detection, text detection, pose detection, and many more. There are traditional and modern approaches to address object detection problem. So traditional way uses image processing techniques such like HOG, histogram, or oriented gradings, which is basically a feature descriptor. The technique counts occurrence of grading orientation in the localized portion of an image. Its advantage is unsupervised in nature, so not requiring the historical data for training. But it is restricted to the complex scenarios, occlusion, illumination, shadows, and clutter effects. Whereas modern way uses data-driven deep learning models. It is supervised learning, more robust to the occlusion, complex scenarios, and challenging illumination. But its disadvantages include requiring the big data for model training, and also requiring the image annotation, which is quite tedious, expensive, and time-consuming procedure. Fortunately, many benchmark labeled dataset is available, such like the MS Coco, Quartet TTI, Pascal, and V5 for the object detection model training. Thanks to the latest advance of deep learning techniques and also the availability of the much more computing power like the GPU and the hardware accelerating, as well as the smaller, cheaper, and the better cameras and the imaging techniques, the object detection has achieved a significant breakthrough recently. So such AI algorithm and hardware advancement make the near real-time object detection and tracking a reality. So we see nowadays more and more deep learning-based object detection and tracking applications became available for healthcare, driverless car, video surveillance, anomaly detections, robot vision, and many more. All major object detection models are deep learning based, and they can be categorized into two general types, one-stage versus two-stage algorithms. The most important two-stage object detection algorithms including the RCNN, so the region-based convolutional neural network, fast RCNN and the faster RCNN, also the mask RCNN and the GRCNN. Most popular one-stage algorithms including the YOLO, SSD, and the RetinaNet. So just to mention, all the major models we have just mentioned above are the anchor box based, and nowadays some new anchor-free methods such like the FCOS, the full convolutional one-stage methods become available and common. As said, an object detector solves two tasks: object localization and object classification. That is, what objects are where. Two-stage models separate these tasks into two steps to solve. It's accurate but very slow, whereas one-stage models combine both into one single step to achieve super-fast detection speed. So the one-stage the detector has the following architecture components: backbone, neck, and head. Backbone is virtually an image classifier pre-trained with big data, such like the ImageNet dataset with more than 40 million of image samples, then fine-tuned on the detection dataset. Neck component extracts the features of different scales to tackle the scale variation issue, so across the different object instances. And finally, the head components do the actual detection, that is, object classification and bounding box regression. In following, I'm going to give a quick overview on these popular object detection algorithms, which including the RCN family, YOLO family, and SSD family. First of all, just a bit background information. The RCN and the SSD both are based on the VGG as their backbone component, whereas the YOLO uses the darknet as its backbone network. Darknet is actually written in C, which is an open source neural network framework, which is fast and highly accurate for the real-time object detection. RCNN, region-based convolutional neural networks. So RCN is the first model to pioneer deep learning approach to address object detection problem. In the first stage of object localization, it uses selective search with greedy algorithm to propose region of interest in the image. Then in the second stage of classification, only focus on the proposed regions of the first stage outputs. It has associated with a couple of latency issues. Issue number one, because the selective search algorithm is fixed, it has no learning involved, so it is a speed bottleneck. And the second latency issue is the object classification on the region of interest is done one at a time, so it's very time consuming. Fast RCN solves the issue number two by running the CN only once per image to generate a convolutional feature map. And on top of it, faster RCN solves the second issue by replacing the selective search algorithm with a region proposal network to predict the region proposals. So the fast RCN is the fastest and the most accurate algorithm among its family. YOLO, you only look once. YOLO is supposed to be the most popular and real-time object detection framework. So it's free, it's fast, and it's accurate. Because it is a single-stage detector, it can predict the bounding box and the object classes directly from the entire image in one go. So it is also open source, ready to be used out of box, and also can be fine-tuned for the more specific use cases. YOLO has been evolving from the first version to the YOLO V2, V3, V4, and V5, and YOLO R. SSD, single shot detector, is another popular one-stage multiple class detector, combine everything into one single step. It actually is very easy to train and also very easy to be integrated into the solutions. It combines the predictions from the multiple feature maps with different resolutions to handle the object of the various sizes. So besides the basic model, a tiny SSD is also available, only have a small size of 2.3 megabytes, which is even smaller than the tiny YOLO, and is well suited for the real-time embedded IoT object detections with the greatly enhanced deep learning layers. Okay, here let's look at a comparative analysis of various object detection models. The MS Qualcomm dataset is used as a benchmark for like-for-like comparison. So we also use both accuracy and latency as evaluation criteria. In terms of accuracy, we use standard object detection accuracy matrix, AP, the average precision, or the MAP, mean average precision. And for the latency, so actually the prediction latency is decided by the both algorithm and the hardware, which in turn decides the maximum FPS support. FPS stands for the frame per second, that is the video frame rate. So real-world videos FPS typically range from 300 to 1000. The faster the detection speed, the higher FPS a model can support. For example, if an algorithm takes about 100 milliseconds to detect one image frame, it can support 10 frames per second. However, if it only takes like 10 milliseconds to detect, so it can support 100 FPS. So also, we actually give the computing capabilities in the ranking order for all the GPU and the CPU variations of hardware. Here we're just using the same V100 for like comparison. Left side is the latency comparison, and the right-hand side is the accuracy comparison among the various RCN schemes. In the left side, you can see the RCN takes about 49 seconds for one image frame detection, which is very slow. And the fast RCN is significantly improved latency to only about 0.2 seconds, and is also the most accurate algorithm showing on the right-hand side. Okay, this is the comparison between the various object detection algorithms. Latency-wise, we can see the YOLO is the fastest, followed by the SSD and the RCN. And then, general speaking, the models that fall into the light blue areas are considered the real-time object detector, capable of supporting like 30 plus FPS. Accuracy-wise, we can see that RCN and the SSD family, such like the efficient DAT, can achieve better accuracy than the YOLO, but they run at a speed of less than 30 FPS on a V100 GPU. On the other hand, the YOLO is also able to run at the much higher speed, more than 60 FPS, which still have a very good accuracy. So besides, the efficient DAT D0 to D4 belong to the SSD family. Here is a summary of major hyperscalers cloud computer vision APIs and frameworks, including Google Cloud Platform GCP Vision API, also the detection tool coming from the Facebook AI Research, as well as another famous one from the Amazon AWS recognitions, and also the IBM Watson visual recognitions and the Microsoft Analyze Image API, and many more. So there are also many open source object detection libraries and the toolkits available, such as OpenCV, an open source computer vision and machine learning library for accelerating the application development with more than 2,500 optimized algorithms, and also it is BSD licensed, making it easier for business to utilize, adopt, and modify the code for specific use case. Image AI is another free and open source Python library to allow people to build a computer vision project with a few lines of code using the PyTorch as a backend. TensorFlow 2 detection model zoo provide a collection of the pre-trained models for the object detection detections out of box, and also support the transfer learning on the customized dataset. So also like the leap face detections, open source library for face detection with pre-trained convolutional neural network models written in the C++, and Genius Face Filter, a lightweight, robust, and real-time face tracking JavaScript library designed for the augmented reality applications, and so on. So face recognition is the simplest facial recognition APIs for the Python and the command line tool, and also the Deep Face Lab is a open source, deep fake system, for the face swapping in the videos. It is believed more than 95% of the deep fake videos actually were created with it. Also, the rest visions and useful for satellite area and the other larger drone sets images object detections. SOD, another embedded and modern cross-platform libraries for the computer vision and machine learning for the IoT and the other systems. And also the Darkflow, Gloom CV, and many more. Computer vision is a relatively mature area in terms of AI democratization. However, object detection is not yet a fully solved computer vision problem. For example, dancing detections, small object detection is still challenging, where a huge gap exists in detection accuracy between the normal and the small objects. So trade-off between the accuracy and the speed is quite hard to achieve. It is because the deeper the neural network architecture it is, the higher the accuracy. But in the meantime, that also demanding the more data and the computing power, therefore slow down the prediction. Among all, we believe the fast RCN is actually the well-performed can be acted as a baseline for the accuracy because it's trained with a diversity of different dataset with different object instance and the skills. Also, if we need some balance between the accuracy and the speed, just consider use the RetinaNet or the YOLO as a good candidate. Also, a lot of the emerging techniques and the algorithms is coming, such like the super resolutions, and it is proposed for solving such kind of the dancing detection scenarios. Here comes the summary and our recommendations. For the object detection, we believe there is always a trade-off between speed and accuracy. So speed-wise, generally speaking, YOLO is faster than the SSD, which in turn faster than the fast ICN. Accuracy-wise, generally speaking, fast ICN is better than SSD, which in turn is better than YOLO. So YOLO actually shows the best overall performance among all the candidate algorithms I have been looking at, closely followed by the SSD with a good balance between the speed and accuracy. So as we know in the data science, no one size fits all. The algorithm choice really depends on your specific use case, scenarios, and the project, and also your business requirements and the KPIs. So different projects is actually the call for the different algorithms because they are actually can thrive in the different tasks. So if you are start to take off a near real-time application like the live video feed analysis, just consider the YOLO as a good starting point. So if your application is not so time critical, but you require high accuracy for the prediction, or just like some challenging small object detections, just consider using the fast ICN as a good baseline. So also, if your project is related to the embedded IoT object detection scenarios, try to use tiny SSD or tiny YOLO and more. So in following sessions, I'm going to get hands-on, actually show you how to using the YOLO V3 and the V4 to make object detection on both images and the videos. Check it out. Before that, leave a like and or subscribe to my channel if you found my tutorial is useful. See you all soon later.